Hello everyone, and welcome back to the CS184 discussion recordings. Today we're going to go over animation and simulation. So what we're going to do is we're going to start here with the worksheet, go over a few questions, and then transition over and write some code. Because we're not going to get a chance to play with animation really in any of the projects. So there's just a little bit of coding during the discussion to give you all some hands-on experience. Okay, so let's get started with the worksheet first and answer these questions. Okay, so the first question, what are keyframes and what do we do with them? Okay, so the name keyframes itself kind of gives you a hint here. And so what keyframes are they're the important frames or the key frames, right, in an animation. So for example, if you wanted to, animate a horse running, you might pick 4 different positions and then take a picture, right? You manually set these positions up. So actually here, you know what? Let's do something else. Let's do a person walking, right? So we might, set one up. Okay, that was a terrible drawing. But one might be one leg here, one leg a little bit in front, and then another one might be one leg back, one leg here. I don't know. I'm not sure exactly how to draw a person walking. Sorry about that. But the idea is that each of these keyframes kind of depicts a different a setup, right? We individually set up these individual joints, what it looks like. And then if we want to get something in the middle here, what we'll do is we'll interpolate between the keyframes on either side of it, right? And this interpolation is generally not linear because typically the type of animation we want to do is more complex. The dynamics are more complex. So not linear, but we'll do some kind of interpolation and get a new kind of position of this model that we didn't manually set up, right? We only had to manually set up 3, and then we can interpolate any number in between those 3 by using kind of both sides and interpolating. Okay, so that's kind of the main idea of keyframes. And so let me just write down the key points. So they're the important points in animation. We interpolate between them to kind of generate the full animation, right? So all the missing frames in between, these are just kind of the key points, and we use interpolation to generate all the other missing frames from the important ones that are done by hand. Okay, and so this process of interpolating is called tweening. Okay, just terminology, not super important, but just good to know. It's called tweening. That's the specific name for this interpolation between keyframes. Okay, so that's what keyframes are. Let's go ahead and keep going. Okay, so what is the difference between forward and inverse kinematics, and what are some problems associated with the latter? So what are some problems associated with inverse kinematics, right? So the way I like to think of this in forward and inverse kinematics is basically to imagine a hand, right? So let's say this is the shoulder and then the hand, and that's the elbow, right? And so what forward kinematics does is we'll say, hey, let's say we have this axis here, and what we'll say is we'll give it the angles that each of these is at, right? So we'll give it the angle of the upper hand relative to this normal. We'll give it the angle of the elbow. So, we'll give it this angle, we'll give it that angle. And then we'll say, what is the final position, right? What is the point here? Or that's, we know that because we're giving it the angles, and that's how we know exactly where this is drawn, right? So we give the angles, the computer draws the final position based on the angles given to it, right? And what inverse kinematics is it's basically the opposite of this. So what we'll do is we'll give only this position. We'll say we want the wrist to end up at this XY position, and then the computer will go ahead and compute the joint angles, the joints for the elbow, joint for the shoulder, angle for the elbow, angle for the shoulder, that puts the arm in whatever final position that we want, that we gave it, right? So forward kinematics is basically we provide the angles, computer determines the final position, and inverse kinematics is we provide the final position and the computer computes the angles needed to get to that position. Okay, so let's write this down. So forward we provide angles, and inverse we provide the final position. Okay, and in both cases, what we don't provide, the computer calculates for us. So in the forward, computer calculates the final position, and inverse, computer calculates the angles. Okay, so now let's talk about some of the problems, right? So what are some of the problems associated with inverse kinematics? And there's a few kind of key ones. So one of them is that for any final position, there's not necessarily just one way to get there, right? So in this case, let's say I'd given it this final position. Here, I'll switch to red. Well, we could have also done, maybe the shoulder was there and then the elbow was there, right? And so it's the same final position, but with different angles for the shoulder and the elbow. So basically there's multiple possible solutions. And one might be better than the other, but the computer doesn't necessarily have any way of telling that. So it's just going to give us one solution, and that may not necessarily be the solution that we want, right? Another issue is that sometimes there's no solution, right? Sometimes it's not possible, given the constraints of the joints, to find the angles necessary to get to a final position. And another problem is sometimes it's not realistic, right? So in the case of a hand, if we think about it, our elbows, they can flatten and they can kind of bend in so that your lower arm is touching your upper arm, but you can't go the other way, right? So if suppose we gave a final position that required that, well, the computer might not know, and it might just give us an angle that is in fact not valid at all, right? So these are just some of the issues with inverse kinematics, which require sometimes, if you're using inverse kinematics, to kind of take a look at the results given back to you and see whether it's feasible, whether it's reasonable, whether it works, that sort of thing. Okay, so I'm just going to real quick try to fit in. So multiple solutions, no solutions, or not realistic solution, right? And so these are the issues with inverse kinematics, right? The multiple solutions, no solutions, it's not realistic, so often requires a little more work to get what we want. Okay, so that's forward and inverse kinematics. Let's keep going. So next is we're going to talk about the Euler method, which is essentially a way to calculate the position of an object given kind of some rules about the velocity and acceleration. Kind of, if we know how to calculate the acceleration, we can basically use this technique to calculate the position at any time, right? And so it's called the forward, or also the explicit Euler method. And these are the update rules, basically. So x here is the position. So x at t plus some delta t. Generally, delta t is a very small time frame, right? And I'll talk about the y in a second. So x at t plus delta t is equal to x at time t plus delta t times the velocity at time t, okay? And similarly, the velocity at times t plus delta t is equal to the velocity at times t plus delta t times the acceleration at times t, okay? And so we generally want this delta t to be small. And the reason for that is because oftentimes the velocity and acceleration are functions of t, right? So they're not constant. But what this rule assumes is that those values, acceleration and velocity, are constant for the delta t period of time. So if delta t is small, this is a relatively reasonable assumption. If delta t is almost instantaneous, you can assume that sure, the acceleration and velocity are not going to change much. But on the other hand, if delta t is large, then that assumption kind of breaks apart, and in general, our animation will not be as realistic because the values we're going to get out for position, for future velocities, are not going to be very realistic. Okay, so let's look at these answers. First, let's talk about some pros and cons of this method, and then we'll go ahead and get some practice in part B. Okay, so let me start with part A. Pros. Right, it's simple. That's simple and easy to compute, right? As you saw, there's just literally the two equations, no complicated manipulations. It's just addition and multiplication, very simple, easy to compute for computers, for everything, it gets us close, right? But then let's look at some cons. And let me add one more, gets us close. So, it might not be perfect, but it'll get us pretty close to the values that we're actually looking for, right? But let's look at some cons. So one of the big cons is that it's often inaccurate, right? As I mentioned, there's an underlying assumption when we use this, and that is that those values for velocity and acceleration are not changing over that delta t time period. So given, with different delta t's, this method could be either really inaccurate or pretty accurate. It varies a lot. So it can be inaccurate, and also it's often unstable. And what that means is it'll lead to basically divergent results. So there'll be a little bit of error, right? Let's say, we do one update step, and that assumption that the velocity is the same isn't quite true, but it's, so then the position we get is a little bit off. And then we do it again, so then the position is a little more off, right? Because it was already a little off. And then we do it again and again and again. And every time we do this, that assumption we make of velocity staying the same is not quite true. So every step we take, we add a little more error into our estimate of position until eventually, after enough time steps, our estimate for position isn't even anywhere close to what it should be, right? Essentially, we've diverged from the result. We're just going farther and farther away and not getting closer at all. So unstable, and another way to write that is can diverge as errors accumulate. Okay, so it's a pretty good method. It's a simple method, nothing too complicated about it, but at the same time, it's not the most accurate method. So it's essentially a trade-off between accuracy and simplicity. And so there's a few other animation methods that are often kind of more accurate, but then those will also bring in some added complexity. Okay, so those are the pro-cons of the forward or explicit Euler method. Okay, so now that we've talked about some of the pro-cons, let's go ahead and do a practice problem, right? Just see how it works to really get some hands-on experience. So say we have a particle with mass 1 at starting position, x at time 0 is equal to 0, 1, with initial velocity -1, 0, and no initial acceleration. Okay, the particle is at one end of a spring, whose other end is the origin, 0, 0, and whose spring constant is k equals 1, and the rest length is 1. Okay, calculate the particle's position at t equals 3 using the explicit Euler method with time step delta t is equal to 1. Okay, so delta t is equal to 1. So let's come down here and let's rewrite some of the facts they gave us, just because we won't really be able to see the problem. Okay, so that's 0, 1. X prime at 0 is equal to -1, 0, and the acceleration at time 0 is equal to 0, 0, right? No acceleration. Okay, so now what we can do is we can calculate the position at time 1, right? Because all we need for that is position at time 0 and acceleration at time 0. So x at time 1 is equal to x at 0 plus delta t times x prime at 0, right? So that's going to be equal to 0, 1 plus, remember 1 because delta t is 1, times negative 1, 0. And so that's going to be equal to negative 1, 1. Okay, cool. So right off the bat, we have the position at time 1. And now what we want to find is the velocity. Well, the velocity at time 1 is also pretty simple because, velocity, we could set up a very similar equation, except in this case, the acceleration is 0. So the second term drops out. And so we know that the velocity at time 1 is actually going to stay the same. Okay, so there we go. We have the position at time 1 and the velocity at time 1. And so now let's get to the interesting part, and that is the acceleration. Okay, so we have a few different things here. So we need a few different equations to set this up. One of the first equations is, if any of you have taken physics, you'll probably have seen this equation. You might have seen it anyway. F equals ma. That's a classic, right? So force is equal to the mass times acceleration. And then there's another equation, and this is specific here because we were told that the particle is at one end of a spring, okay? And so that is F is equal to kx, where k is the spring constant, which is given to us, and x is the displacement, okay? This is important. So so the spring has some natural rest length. Basically, if you apply no force to the spring, it'll be some length L. And so if we pull on it by, some extra length x, that is what's going to affect how much force is put on the spring, not in fact how long the spring is. It's how long it is relative to the rest length. Okay, so given this now, we're interested in this value, this a value, this a quantity, right? We want the acceleration. So what we can do is we can do a little bit of a rewrite, and we can write a is equal to f over m, right? And then we can, once again, now we can take this equation, plug it in, so we get kx over m. And then what I'm going to add here is, I'm going to say times u. And what this u is basically, if you think about it, right? F, force, that's a scalar. Mass is a scalar. So, but our acceleration is not a scalar, right? Acceleration is a vector. It has a direction. And so the way we give it that direction is by multiplying by u, which in this case is a unit vector, in the direction of the acceleration. Okay, and the direction of the acceleration for a spring is always going to be towards its natural length. So if it's, natural length is 1 meter and I pull it to 1.5, it's going to pull me back in the direction of its natural length. Meanwhile, if its natural length is 1 and I, squeeze it down to 0.5, it's going to pull me back to 1. Okay? So now that we have this kind of equation set up, let's go ahead and plug in some values and see what we get, okay? So a, and I'm going to write this in our standard notation, x double prime of at 1 is going to be equal to, okay, so let's do this. First of all, k, what is k? If we come up here, spring constant k is equal to 1, nice and easy. So that's 1 times, okay, now we want to find the displacement. We were told over here that the rest length is 1. So let's find, and the origin is 0, right? So now let's find, well, where is our particle? It's at negative 1, 1. So the spring essentially is going from 0 to negative 1, 1. And if you, do the math, use the Pythagorean theorem, it's 1 squared plus 1 squared square root. So that's going to be 1 plus 1 squared, so 2. And so this is going to become square root of 2 minus 1. Remember, because I said it's the displacement, not the absolute length. So square root of 2 is the absolute length. We're going to subtract the rest length, which is 1. All over the mass, which if we come back up here, mass 1, right? Nice and easy. Put the 1 there. Okay, now the interesting part, the unit vector, right? So which way is this going to go? Well, we're longer than the rest length, right? We've pulled it, we've stretched it apart, so it's going to want to go back in that direction. And so what we do is we're going to write 0, 0 minus negative 1, 1, right? And then in order to make it a unit vector, we're going to put the norm of that in the bottom. Okay, so there's our equation for the acceleration at this time step. And so here we go. I'm going to skip through some of the math for the sake of space and time. But if you do the math over here, what you're going to get is that the first term is going to be root 2 over 2, and the second one is going to be negative root 2 over 2. Meanwhile, over here, we have, the ones drop out, and it's just going to be a root 2 minus 1. So what we're going to have is root 2 minus 1 times root 2 over 2, comma, negative root 2 over 2. And if we multiply that out, we're going to get, a bunch of math, but it's going to be 1 minus root 2 over 2, and then it's going to be root 2 over 2 minus 1. Okay, so there we go. We found our acceleration at t equals 1, right? We set up the f equals ma and f equals kx equations, then did some manipulation, plugged in the kx, multiplied by the unit vector, which is important in this case, and then solved out to get our final acceleration. Okay, so now that we have this, let's keep going. I ended up using a lot of space, but that's okay. So what are we interested in next? Now we want the position, should not have added the dot, at time 2, right? And this is very similar to what we did up here, right? We're going to take the position, delta t, add the velocity. So position is now negative 1, 1. Delta t is still 1. Velocity, you can see, is negative 1, 0. So this is going to be negative 2, 1, right? Nice and easy. Meanwhile, same thing for this velocity. We're going to take the velocity and then add it to 1 times what we calculated over here, this 1 minus, right? So what we're going to do is, so if we add it up, x prime at 2, negative 1 plus 1 minus root 2 over 2 is just going to become negative root 2 over 2. And then the second one is 0, so it's just going to stay the same, root 2 over 2 minus 1. Right, and there we go. We've found the position and velocity at times 2. And now keep in mind that we're interested in the position at time equals 3. So at this point, it's not necessary for us to calculate the acceleration anymore, because we're not interested in the velocity at time 3. We only want the position. And all we need to calculate the position at time 3 is the position at times 2 and the velocity at times 2. Okay? So given that, let's go ahead and find the position at time 3. Sorry about that. Okay, so it's just going to be this position plus 1 times the velocity. And so that's going to be negative 2 minus root 2 over 2 and root 2 over 2, because it'll be plus 1 minus 1. And there we go. That is our answer. Okay, so let's look at what we did here. We started with these givens. We used that to calculate the position and velocity at time equals 1, right? Just following the Euler formula. And then we found the acceleration using f equals ma and f equals kx together. Once we had found the acceleration, then it was relatively simple, because we could calculate the position again using the position and velocity we found in the last time step, calculate the velocity, and then using that we calculated the position. Okay, so a simple application of Euler's formula, but this is good practice. It may be something you have to do on an exam, so good stuff to practice. Okay, so that is all for the worksheet part of the discussion. Next, we're going to go and do a little bit of coding to get some hands-on experience.